Okay, so today I'll be presenting on wind resistant building design towards saving lives and property. So, what is wind? On the surface of the earth, wind consists of the bulk movement of air, the full nature of which is not fully understood, but two major contributory factors that can be given are convection currents caused by air being warmed at the earth's surface, becoming less dense, rising and being replaced by colder air. Transference of air between high and low pressure areas. Building design. Good wind performance depends on good design, including detailing and specifying, materials application, maintenance, and repair. A significant shortcoming of any of these five elements could jeopardize the performance of a building against wind. Design, however, is the key element to achieving good performance of a building against wind. Design inadequacies frequently cannot be compensated for by the other four elements. Good design, however, can compensate for other inadequacies to some extent. Wind resistant building design must include a strong continuous load path that holds the roof, walls, floors, and foundation together and protects against flying debris during an intense wind event. Many factors must be taken into account before the magnitude and direction of wind pressures can be determined. These include the height to width ratio of the building, the length to width ratio of the building, the plan shape of the building, the approach topography, exposure of the building, and the proximity of surrounding structures. The steps for building design. First one is calculate loads. Calculate loads on the main wind force resisting system, which are the primary structural elements such as beams, columns, shear walls, and diaphragms that provide support and stability for the overall building. The building envelope and rooftop equipment in accordance with the local building code or whichever procedure results in the highest loads. The importance factor for most buildings will be 1. However, for some office buildings, it may be prudent or required to use an importance factor of 1.15. And a note that should be taken is that in the past, architects didn't perform load calculations on the building envelope, which are roof and wall coverings, doors, windows, and skylights, and the rooftop equipment. And as a result of not determining loads and designing adequate load resistance, building envelope and rooftop equipment failures have been the leading cause of failure during past wind events. It is critical that loads be determined by the architect or engineer for the building envelope and rooftop equipment and make sure they are designed to accommodate the design loads. Second step, determine load resistance. After loads have been determined, it is necessary to determine a reasonable safety factor or reasonable load factor. For building envelope systems, a minimum safety factor of 2 is recommended. For anchorage of exterior mounted mechanical, electrical, and communications equipment, such as satellite dishes, a minimum safety factor of 2 is recommended, unless an importance factor of 1.15 is used. If a 1.15 importance factor is used, a minimum safety factor of 3 is recommended for anchorage of exterior mounted mechanical, electrical, and communications equipment. For structural members and many cladding elements, load resistance can be determined by calculations based on test data. For other elements, such as most types of roof coverings, load resistance is primarily obtained from system testing. Detailed design. Design, detail, and specify the structural system, building envelope, and exterior mounted mechanical, electrical, and communications equipment to meet the factor design loads based on appropriate analytical or test methods. As part of the detailed design effort, load path continuity should be clearly indicated in the contract documents. Load paths need to accommodate design uplift, racking, and overturning loads. Load path continuity obviously applies to main wind force resisting system elements, but it also applies to building envelope elements. And this figure illustrates load path continuity of the structural system. Members are sized to accommodate the design loads, and connections are designed to transfer uplift loads applied to the roof and the positive and negative loads applied to the exterior bearing walls down to the foundation and into the ground. The roof covering is also part of the load path. To avoid blow off, the non-structural elements must also be adequately attached to the structure. And something to take into consideration is that connections are a key aspect of load path continuity between various structural and non-structural building elements. For example, consider a window. The glass must be strong enough to resist the applied load, and the glass must be adequately anchored to the window frame, the frame adequately anchored to the wall adequately anchored to the foundation, and the foundation adequately anchored to the ground. As loads increase, greater load capacity must be developed in the connections. Durability. Because some locales have a very aggressive atmospheric corrosion, special attention needs to be given to specification of adequate protection for ferrous metals, or specify alternative metals such as stainless steel. In some locales, termites present a significant threat to building performance. Where termites are problematic, it is recommended that the soil be treated with a termiticide applied by a professional company experienced in termite treatment. Rain penetration. Although prevention of building collapse and major building damage is the primary goal of wind-resistant design, consideration should also be given to minimizing water damage and subsequent development of mold from penetration of wind-driven rain. To the extent possible, non-load-bearing walls and door and window frames should be designed in accordance with rain screen principles. With this approach, it is assumed that some water infiltration will occur. And here are some pictures demonstrating what wind can do to buildings. And here in the picture on the left, the metal wall covering was applied to plywood over metal studs. And here you can see the metal stud wall collapsed. And in the picture on the right, the wall seems to be unreinforced, and this caused it to collapse. And it could have been during a storm that had wind speeds that were less than the designed wind. In these situations, not only are the buildings damaged, but the property as well, and the people definitely get injured or perhaps die as well. And now I'll be playing a short video.
We've all seen the damage that can occur when Mother Nature blows high wind speeds at our homes. If there's any good news that can come out of these storms, is that it pushes us to find better ways to build stronger, more wind-resistant homes. Today I want to show you some of the technology that we build into our homes to counteract these high wind speeds. We're going to take a look at a couple of homes in a coastal region that are in a high wind speed zone. So let's get out in the field and let's take a look. On this house here, the first thing we notice is the structural grade sheathing on the exterior walls that have been secured with the proper nails and locations. The sheathing works to hold the wall studs, plates, and headers together. Okay, here we see the bottom plate on the wall is secured to the foundation with bolts that have been embedded into the foundation concrete. Then we have the metal connectors that tie the wall studs to the base plates. In the old days, there were just a couple nails holding these together. The metal straps used here tie the top of the wall together. So when high wind speeds apply pressure to this home, we want the house to be tied together from the foundation to the roof to hold all of these different components together. Here, a large connector has been embedded into the concrete foundation, and it will eventually be secured to the corner of the home. You can see the massive number of fasteners that hold this connector to the house. Here's a roof truss to wall connector. Again, the metal strap needs more nails and will eventually wrap under the doubler plate to tie the roof framing and wall together. You can see how many holes are in this connector that are going to be filled with nails, trying to counteract that massive force from that wind on the side of this building, trying to pull that roof off. This large steel connector ties the wall down to the foundation with an anchor that's embedded into the concrete. Lag bolts are used for the connection to the wood framing. This strap that runs diagonally across the wall is called let-in bracing. It's also called rack bracing, which prevents the wall from racking. In other words, it prevents the wall from being pushed out of square. This is another method for holding the house in place when wind loads are applied. So you can see we've come a long way in building stronger homes. We went from using just a couple nails per stud and rafter to now using some serious engineered connectors that have been tested to withstand some heavy wind loads. So I think we can all agree that sometimes we're happy that we don't build them like we used to.
Okay, and that was the end of my presentation. Thank you for listening.